Welcome to today's lesson on calculating magnification and estimating the size of subcellular structures. Today, we are going to learn about microscopy and how to accurately convert microscopic observations into meaningful data. In our lesson today, we will cover two main objectives. First, we will learn how to use the formula for magnification, which includes calculating the actual size of cells and their components based on the observed image size and the magnification level. We will also look at how estimations can help us to judge the relative size or area of cells and subcellular structures. So far, you have learned that cells are incredibly small structures, often requiring a microscope to see. You should also be familiar with expressing numbers in standard form and using different prefixes such as milli, micro, and nano. This foundational knowledge is crucial for understanding today's lesson, as it will help you to perform calculations involving magnification and to understand the scale at which cells operate. Being able to accurately measure and interpret the size of cells and their structures is essential for many fields, including microbiology, medicine, and biotechnology. These measurements help scientists to understand biological processes and observe and record life at the cellular level. Let's get started. Being able to accurately measure and interpret the size of cells and their structures is essential for many fields, including microbiology, medicine, and biotechnology. These measurements help scientists to understand biological processes and observe and record life at the cellular level. Let's get started. Magnification is a key concept in cell biology that allows us to understand the size of cells and their subcellular structures when viewed under a microscope. The formula for magnification is straightforward and essential for interpreting microscopic images. Here's how we can make sense of it. The formula is the magnification is equal to the size of the image divided by the size of the real object. Often, you'll be given two data values from this equation, and you'll then need to find the third. You may find it helpful to visualize the relationships between the three variables by using a triangle. This helps us to recall how to rearrange the formula depending on which data value is left for you to find. On the triangle, cover up what you need to find to rearrange the equation. This will give you the following three equations. The magnification is equal to the size of the image divided by the actual size of the object. The image size is equal to the magnification, multiplied by the actual size. And finally, the actual size is equal to the image size divided by the magnification. Before we apply the formula, it's crucial to ensure that all of your measurements are in the same unit. Microscopic measurements often involve converting between units such as centimetres, millimetres, micrometres, and nanometres. Because of this, let's remind ourselves of the following common conversions. 1 metre is equal to 100 centimetres, while 1 centimetre is equal to 10 millimetres. 1 centimetre is also equal to 10,000 micrometres. Then finally, 1 centimetre is equal to 10 million nanometres. Let's look at two different examples to understand how to apply the magnification formula, as well as unit conversions. Firstly, let's try finding the magnification. We are given an image of a palisade cell that is 7 centimetres in length. However, we are told its actual size is 70 micrometres. Let's use the formula to calculate the magnification of the image. First, we must convert the actual size of the palisade cell from micrometres to centimetres. 70 micrometres in centimetres is equal to 70 divided by 10,000. This equals 0.007 centimetres. Now, we need to apply the magnification formula. Since the magnification is equal to the size of the image divided by the size of the real object, our magnification in this case is equal to 7 centimetres divided by 0.007 centimetres. This is equal to 1000. Therefore, the magnification is times 1000. Now, let's look at a second example where we are finding the actual size of a subcellular structure. We are given an image of a mitochondrion that is 2 centimetres in length. However, we know that the magnification of the image is times 2000. How do we figure out the actual length of the mitochondrion? We can use the magnification formula, after we have rearranged it, to find the actual size of the mitochondrion. Since the actual size of the mitochondrion is equal to the size of the image, divided by the magnification, we know that the actual size is equal to 2 centimeters over 2000. This equals 0.001 centimeter. Next, we need to convert this to micrometers. 0.001 centimeter in micrometers is equal to 0.001 multiplied by 10,000. This is 10 micrometers. Therefore, the actual size of the mitochondrion is 10 micrometers. In addition to precise calculations, we often need to estimate the size or area of cells and subcellular components. Using geometric shapes simplifies these estimations. Here are some examples of estimations that we can use when calculating the size of cells. When estimating the size of a red blood cell, we can assume that the shape is approximately circular. Therefore, we can use the formula for the area of a circle to estimate the size of a red blood cell. To remind you, this equation is the area of the circle is equal to pi, multiplied by the radius of the circle squared. When estimating the size of palisade cells, we can assume that the shape is roughly rectangular. Therefore, we can use the formula for the area of a rectangle. To remind you, this is the length multiplied by the width of the rectangle. When we are working with microscopic images, we must always be sure that all of our units are consistent across all measurements. We make sure to accurately convert our units before applying the magnification formula, and we only use the magnification formula to calculate either the magnification, the size of the image, or the actual size of the object. Let's work through some more questions to consolidate our knowledge on magnification. Here is our first question. A magnified image of a mitochondrion is 2 millimeters long when viewed under a microscope at a magnification of 1000. What is the actual size of the mitochondrion? Pause here to have a go yourself. Now, let's walk through the answer together. Firstly, let's recognize the key information. The size of the image is 2 millimeters, and the magnification of the image is equal to 1000. We now need to apply the rearranged formula to figure out the real size of the mitochondrion. The real size of the mitochondrion is equal to the size of the image divided by the magnification. Hence, the size of the real object is equal to 2 divided by 1000. This is equal to 0.002 millimeters. As such, the actual size of the mitochondrion is 0.002 millimeters. This can also be given as 2 micrometers. Let's look at one final question. The size of a bacterial cell is given as 2 times 10 to the minus 6 meters. Under the microscope, it appears as 0.2 centimeters. Calculate the magnification in standard form. Pause here to have a go yourself. Let's recognize the key information. The size of the image is equal to 0.2 centimeters, and the size of the real object is given as 2 times 10 to the minus 6 meters. Next, we will convert units. To convert 0.2 centimeters to meters, we need to do 0.2 divided by 100. This is equal to 0.002 meters. Now, we must convert out of standard form. 2 times 10 to the minus 6 meters is equal to 0.000002 meters. Next, we can apply the formula. The magnification is equal to the size of the image divided by the size of the real object. Hence, the magnification equals 0.002 meters divided by 0.000002 meters. This is equal to 1000. Finally, we will convert back into standard form. Since the question asked us to, 1000 is 1 times 10 to the 3 in standard form. In conclusion, the magnification is 1 times 10 to the 3. By using these steps, you can effectively tackle GCSE Biology questions related to calculating magnification, converting units, and using standard form. In today's lesson, we focused on measuring sizes and estimations within cell biology. Particularly, we looked at how to use the magnification formula and express our answers in standard form. We started by discussing the importance of understanding cell sizes, as well as subcellular structures, as this knowledge is fundamental in various aspects of biology. We then examined the magnification formula, which is the magnification is equal to the image size divided by the actual size. This formula is crucial for calculating the magnification required to view cell structures clearly under a microscope. We practice using this formula with different examples to ensure that you are comfortable with the calculations. We also covered how to make estimations to judge the relative size or area of cells and subcellular structures. Estimations can often provide a quick understanding of proportions and scales, which is helpful in both practical laboratory settings and theoretical contexts. We went over some examples to practice making these estimations. You should now be able to effectively use the magnification formula, express your answers in standard form, and make useful estimations about cell sizes and structures. These skills are essential for analysing and understanding microscopic images, and will be foundational as you progress in your studies of cell biology.
Watch the rest of the GCSE Biology course at Sophos Education.